Alright, so today we're going to finally write
You actually have notes with you today, huh?
Yeah, I've been working on the train and writing these things down. There's so many definitions and I want to do them in the right order that I don't want to mess it up. Okay, so we're talking about contours. Before we do that, I wanted to finish our discussion from the end of class yesterday about the Jordan curve theorem.
Yes.
Because there's something really neat that I posed as a problem, but which...
Wait, did Jordan invent that theorem?
It's a good question. So
And who is Jordan?
Michael Jordan.
Not Michael Jordan. So
Why not?
Why wasn't it Michael Jordan?
Yeah.
That's sort
He's
of
a mathematical genius.
almost.
Hey, he uses it in his basketball.
Okay. So
Although he might not know it.
Why don't you just draw like the genie coming out of the lamp?
that's right. Here's the thing. If I put up this piece of paper, I mean, actually, you can kind of forget what's.
Then we don't know the inside or the outside either, though.
Do you?
Yes, we do. Look at the top.
Yeah, but what if you do that in the middle?
So let me put a point right there. Is that in or out?
In.
Oops. Now it's nothing.
No, it's not because there's no in or out because the sides are broken.
Oh. How could we tell? Well, check it. If you were over here, this point right there, is that in or out?
In.
How do you know it's in? I mean, you can't see any more than you can below, but
But what if you're in the
That's
middle
out,
and
right?
you really don't know?
Yeah,
you know
that's
that this is out. So you cross one line, you must be in. If I cross another line, over here, what am I?
out.
I'm out. Cross another line, I'm in. Cross another line, I'm out. Another line, I'm in. Another line, I'm out. Another line, I'm in. So this
Just like
must be-
skinny jeans.
And now you're
What
right.
is with that?
No, but if you're in the middle, then you really don't know.
Anywhere, we didn't know. I mean, this is in the middle. Yeah. All you have to do is count.
No, I know, but let's say you had it
I bet
this,
Hey, okay, you're saying if I covered up all
like
sides
this, and then like this,
and then like this,
then you'd have no idea.
that's right. So
I don't think
if
anyone
you
else
get rid of all escape routes to the outside
Then
world,
you have no idea.
then you're right. You can't really tell. That's absolutely right. But if you have a path that goes from where you are to the outside,
Well, yeah, then
right?
that's-
Even if you cover up these two, but but remember when I first posed that problem, your answer was no, we don't know, right?
But now we know.
Now you know, right? Okay. And this is
What do we?
I think what I'll do is I'll send you a puzzle. Has anybody in here ever played Slitherlinks?
I've done puzzles.
Okay, Slitherlinks is a puzzle which, well, it's existed for quite a while, but it regained some popularity in recent years because of the Sudoku craze. Right, a lot of puzzles are like Kakuro is the same thing. That's been around for years with a different name.
What is it called?
So the one that I'm talking about is Slitherlinks, but Kakuro is we give them these pseudo-Japanese names because it makes it sound more impressive. You know, Sudoku has been in Dell magazine as number place for years, and then all of a sudden they gave it a new name in Japan, called it Sudoku, went to Britain, got really popular, came over here, and all of a sudden like, oh my gosh, how come nobody ever thought of this game before? And it's been around since I was born, right? Okay, so there's a game called
That
Slitherlinks.
long, huh?
And Slitherlinks is, thank you very much. I actually enjoy Slitherlinks more than Sudoku because you don't need to ever write in numbers or anything. You don't have to keep track of much. But what's really neat about the game is that a strategy tool, I mean, a way of solving puzzles is to use the Jordan curve theorem. Right? Knowing, because in that puzzle you build a path, right? And that path it's just a continuous loop, basically. Looks just something like this, right? Except the lines aren't cut off. And
it's not continuous.
And there's an inside and there's an outside. And so each little square on the grid you want to decide, is this inside the loop or is it outside? And you can tell if you have enough lines by just counting till you get to the border. And if the number, well, let's see, if it's an odd number of them,
You're inside.
then you're inside. If it's an even number of them, then you're outside. So this is kind of neat that you can apply such a heavy-duty theorem in such a silly little puzzle. I'll send you some versions of it. It's really fun. Okay, so I just wanted to mention that. Jordan is probably how his name was pronounced.
Is he Gordon Blue's brother?
Gordon Blue. Gordon Blue.
We said it French.
Like Dijon?
Dijon Mustard.
So there's been a controversy over the years as to whether or not he really gave the first proof of the theorem. He was not the first one to write it down.
He was the first one to prove it?
I think he really was the first one to prove it, but his proof, some people thought, oh, it's not really a good proof, but I think...
Technicality.
I think the consensus is actually it's fine. Because what happened is later on another mathematician came around and said, oh, his proof leaves out a really important case. He doesn't even mention it really. And so he's kind of missing the whole point. And it turns out that that case that he's not mentioning is almost trivial and really is not important to his argument anyway. So that guy created some controversy. But, yeah.
He wants some credit.
Yeah, everybody wants the credit. But you know what it is, you either do the work or you get the credit.
Or you do the work and you don't get the credit. But you're humble enough not to.
No, you either do the work or you get the credit.
Oh.
Yeah.
No, but there's people that do the work and don't get the credit.
That's what I'm saying. You either do the work
or
you get the credit. It's an either or. It's like the or at Olive Garden. When you go to Olive Garden and they say you can get a super salad. And I said, yes, I'll take both. And they said, no, it's either. And I said, it doesn't say either, and that's a mathematical or. So they just gave me the salad.
Oh well, it was worth a try.
Yeah. Okay. So how about some math? All right. So yesterday
Is this thing on?
I think so.
But on all of them.
So yesterday we wrote down definitions of things like a smooth curve in R2, a simple curve, a closed curve. We talked about orientation, positive orientation, negative orientation.
I had a question on the homework.
We'll talk about homework at a different time. We're going to do a lecture now.
No, but I seriously have a question on the homework.
That's okay.
Is it bright in here or something?
That's okay. Okay,
No,
so
he's just shining.
the difference between R2 and the complex numbers is that it's actually going to be easier in some ways to write down all these definitions again for the complex one. It'll be actually just a little bit easier. So you might have some curve. Right now we're in the complex plane. Okay, and we started really looking at these kind of issues already.
What's wrong with that?
And you have... What's wrong? Because of the
It's
marker?
dying.
The marker is dying. Unfortunately, I didn't bring my bag up, and that's where all my good markers are. We'll try the blue.
I have markers too.
You might need to get them out. Alright, so we have a path. Okay, I'm not a good tracer. If I do the other one in red, though, it'll be in 3D.
That's really cool.
Yeah. Alright. And, well, each point on here has a real component to it, right? A real part and an imaginary part. So, that's x plus yi. Okay. And so if we want to write down parametric equations, right? So again, we're going to let time run, and then the x and the y are going to change over time. The same thing. And so we can define the function z of t, and it'll just be x of t plus y of ti. And what's really nice, if you do it this way, the derivative of this function, and we've actually seen this effectively before, is just given by taking the derivatives of the component functions. Right. Those of you who took multivariable calculus already have seen this when you define a vector valued function, that when you want to take the derivative of the vector valued function, you can do it component wise. Okay, we'll see that in a few weeks. Okay, fine. So what do I mean by then, for instance, a smooth curve in the complex plane? Well, what did I mean by a smooth curve in R2? Okay, smooth meant smooth, right? What did it not have? Well, discontinuities are bad already, but in particular, it didn't have these sharp corners, right? It didn't have a corner, it didn't have a cusp. Okay. So, well, what we might say is, let's give a name to this. Let's call this C. Now, today we'll do things in terms of the. Well, okay. Let's say this. This Z of t. Okay. So here t is running from A to B. If it's the case that when, for instance, t is A, then you're, say here, Z of A, and here you're, when t is B, you get Z of B. Then we'll call this a parameterization of C. Okay. So we'll let Z of t. Boy, this is rough.
You're having a rough day today, huh?
I only got 2 hours of sleep last night, and it doesn't hurt my brain in terms of what I can think about, but it really affects the fine motor skills. You know what I mean? It just you're just walking around. That's what happens. So let's let Z of t be a parameterization of C, and remember, we've already done several examples of this. You can have multiple parameterizations of the same curve. Okay. So C is smooth if, well, what do we want? Right. Well, basically we're trying to copy what we did for reals. Okay, we don't want to have corners, we don't want to have cusps. So we want that something about, well, we can talk about the parameterization. So what was our condition? Should be
Continuous.
You certainly want Z to be continuous.
The derivative.
The derivative is continuous.
And the derivatives are never simultaneously zero.
And of course, yes, and that's the second bit, right? We don't want the, so if, well, so we can write it, if Z prime is continuous, or X prime and Y prime are continuous. Okay, so if Z prime is continuous, and Z prime of t, and of course this is on the interval A to B, and Z prime of t is not 0. Oh, yeah. Wait a second, something's not right there. Oh no, it's fine. Okay, good. Okay. What was the other thing what's the next thing that we did? We did smooth.
Piecewise smooth.
And we had piecewise smooth. Okay, well, I'm going to write this down right now. I'll wait to write it down because you kind of get this feeling for what piecewise smooth is, right? You just take a bunch of these things and connect them up, okay? And you don't worry about smoothness at the where they connect. Okay, so we had smooth. You have piecewise smooth.
Simple.
We have simple. So what did simple mean? So C is simple if, what did that mean? This is the one that you could not tell what it meant from the word itself.
Never intersects itself.
Yeah, it did. You don't, right? It's not, there's no multi-points. Okay, there's no point that gets hit twice, except perhaps
The initial point.
right, except for the initial point. So there's an easy way to write this down, and that's just to say if Z of t is 1-to-1 on the interval A to B, and you don't include B. Okay, now does that make sense? Is that right? 1-to-1 means that no two different points go to the same point. Okay. So that says that the curve can't at two different times be at the same place. Okay, that's what we want, right? We don't want that at two different times you're at the same place, except possibly at the endpoints. But we get rid of that possibility by tossing out the endpoint. Right? That's how I wrote it down, but now I don't. Now I'm not happy about that. Why am I not happy about that?
1-to-1.
Well, the 1-to-1 doesn't bother me as much as this half interval thing.
Closed.
Here's what I'm worried about is,
Like B is not included.
okay, so normally this is what it might look like, right? But what if I did this? No, I put B here at the end.
Yeah, then you have a problem.
See, now that's not 1-to-1. I mean, that is 1-to-1 on this interval A to B. So yeah, now I think we need to be more careful. So let's turn this into a square bracket, and then just say except possibly. It's 1-to-1 on AB, except possibly Z of A equals Z of B. Okay. On the homework, I use a phrase, this is for the next week, called an admissible parameterization. And so I better, because it's not in your official course textbook, I better tell you what I mean by that. So, if Z of t is a parameterization of C such that Z prime of t is continuous, right, on AB, of course. Z prime of t is never 0 on AB. And Z of t is 1-to-1, right, on AB. Except, possibly, and Z of A equals Z of B. Then this is what I want to call an admissible parameterization. And of course, what kind of curve is going to be connected to something with an admissible parameterization?
Can you say that again? I'm sorry.
If I have let's say I have a curve, and then I find a parameterization for it. And then I check these three properties, and they all hold. So now I have an admissible parameterization. What can you say about the original curve? What kind of curve is it?
Polynomial?
No. It's all on the board.
No.
It's not a guessing game.
Simple.
Simple, right? Because simple says, it's this last condition,
And smooth.
and smooth. So the only curves that will have an admissible parameterization are simple smooth curves. Okay, so if blah blah blah, such as this, or I should say then, there's a missing word here, then Z of t is an admissible parameterization for the simple smooth curve C. So on the homework, I'll give you And I should say, okay, I probably also allow you to, and I use the word admissible parameterization when you have piecewise smooth as well, right, which is also, it should be simple. Okay, but in any case, on the homework, I ask you, okay, here's, I'll describe some curve, find an admissible parameterization. So it means you need to find a parameterization and then verify that these properties hold. And why do we want these sort of properties to hold? Well, in the end, we want to be able to write down some nice theorems. We need good hypotheses. These are going to be kind of the, well, it's not necessarily the minimum that you need. It's just, it's going to be what we want so that things aren't, we don't have to work too hard. Okay, so now we finally can define a contour. So half of this definition looks very strange. The other half looks like obvious. So a contour, C, is a single point. Okay, that's the weird part. So this is for technical reasons you throw it in. Okay, so or it's going to be thank you. It's going to be a bunch. It's going to be a piecewise simple smooth curve. Okay? You're going to have a bunch of pieces, okay? And each piece has to be simple and smooth. So, or a piecewise simple smooth curve. So for instance, we go here, well, this is a simple smooth curve, no problem with that. Now let's say around here we draw a circle. That's a nice simple smooth curve. And once we get down to the origin, then I go around again to say right there. So I go 3/4 of the way around. Okay. So there's another. So I go around once, and I do another 3/4, and then I come out and go out like that, and I'll end right there. If you're going this way, it might be a roller coaster or something. I don't think you should end up. Well, you shouldn't go around the roller coaster like that, I guess. Oh yeah, this is really a bad idea to do on a roller coaster. Really,
And the other way as well.
yeah.
Like stop.
This is, by the way, this orientation is, is backwards from the way. This is the negative orientation, right? Because you're going the wrong way around the circle.
Mm-hmm.
Yeah, we should, if we want to be positively oriented, go this way around, and then we could.
Wait, where are you starting?
I'm starting here. There's my initial point.
And this is supposedly a contour?
Yeah. Now, why are you bothered by this? You can, and I can anticipate your answer, but tell me, why are you bothered by this?
Because we said it has to be 101.
Ah, right. Okay, it's this word simple. It's simple in here, right? How do we get around this problem?
Piecewise.
Piecewise.
Or a piece. Okay.
So, I almost wrote this up incorrectly. In my notes today, I wrote down simple piecewise smooth curve. Now, to me, a simple piecewise smooth curve actually means it's a piecewise smooth curve, which is simple, which means it's the whole thing is 1-to-1. But by putting the piecewise first, the hyphens are all on this side. It's a simple smooth curve, but then you can come in pieces. So you're allowed to go over. See, we have this this condition about simplicity, right? Makes it 1-to-1. It sounds like it's really limiting what you can do, but the piecewise really gets you back into it. But what's going to be nice is, so let me write in different pieces here. Well, let's see. If we go around once and we go back the other way, that's fine. That'll be C1. The first time you go around this way, that'll be C2. Then you go back around the other way, that'll be C3, and then this last bit will be C4. So this contour is made up of 4 parts. And what's important when you put these together, right, because it's piecewise, initial points and terminal points should line up in the right way. Now, let's say I kept going here. This will be C5. And then I come back here. It'll be C6. And then I can go back up here. This will be C7.
It's like a strange circuit.
Looks like a piano almost.
Oh yeah, with the chair.
Uh-huh.
Yeah.
Yeah. So somebody said it's like a strange circuit. Yeah. In particular, it kind of makes a loop, right? It goes all the way around and comes back on itself.
It's like the battery.
Oh yeah. So
The big loop is the light bulb.
Oh, or the light bulb. Yeah.
you know, by the way, the complex analysis, probably the biggest physical application of it is.
Is electrical engineering.
Oh, that's right. You
told
had
you.
right. Yeah. What kind of a contour should this be called?
What kind of?
Yeah, what should we name it? I mean, this is different. When I stopped here, all right, this thing went, around, and then the last point, the terminal point of the contour, is not the same as the initial point of the contour. But now, when I've connected it up,
It's closed.
it's closed. Exactly. Right? We had this definition yesterday. When the terminal point and the initial point of an arc are the same, then you call it closed, right?
Right. Yeah.
So this one here, let me say, if the initial and terminal points of C. Now, you have to be careful here. All right? C, definitely, there's an order to the way you write these things down. If you wanted to be really precise, you might write that C looks something like this. Gamma 1, gamma 2 through gamma n. Each one of these would be a simple, smooth curve. Right? And it would have a parameterization.
But that's really funny because gamma itself is not a simple smooth curve.
That's true. That's very true. I never thought about that before. Good point.
So should we name it another letter?
No, this is a standard one. That's interesting. So, what do you think the initial point for C should be?
C naught.
Gamma 1.
Not a name for it. I mean, what is it? It's the initial point of
Gamma 1.
gamma 1. What's the terminal point?
The terminal point of gamma n.
Exactly. So there's an order to this, and that's how you determine. So when I say the initial terminal point of C, I mean you take the first curve and take its initial point, and that's the initial point of C. Take the last curve and its terminal point, and that's the terminal point of C. So if the initial and terminal points of C coincide, then C is a closed contour. And we are going to be very interested in closed contours. For instance,
Is it a closed loop?
when we have a closed contour and we start doing integration next week, we're going to be able to state Cauchy's integral theorem. That's right. That's right. We're going to be doing integration everywhere. So, and Cauchy's integral theorem is going to say what happens when you integrate around a closed contour, right, with certain conditions, analyticity conditions.
Then it's 0?
Yeah, that's what it's going to be. And why do you suspect that?
Because the start point is the same as the end point.
Is that a van? Is that a then?
It's a then.
It's a then?
Yeah.
Yeah, then Z of T.
Yeah, sorry, I had to add that in.
I'm so bad with the English language. It's not even funny.
All right, what do we got here? Oh yeah, so let's see. We'll do a little technical consideration. So one thing that we are going to need at various points when we're doing this integration stuff.
Various.
Is we're going to need to know the length of contours. Now, this really shouldn't be that hard.
That was the bonus question, remember? The formula for arc length
Yes.
that I got wrong?
What?
Well, I didn't remember that you got it wrong.
I remember it because I got it wrong.
Yeah, this is true too.
Is that coming back to haunt us now?
Yeah.
Want to show you, I really like your flyer.
So here's the thing. If I have a contour and it's not just a single point, honest to goodness, piecewise, simple, smooth curve, then it's got a bunch of these simple, smooth curves lying around. And if I want to know the arc length, right, the length of this curve, well, would you say it's pretty clear that I should just be adding up the lengths of the individual curves? Now, there's a reason you should say, wait a second, I don't think that's right. And this picture...
Did you say that? Can you say that again?
Yeah, what am I saying? I'm saying
that the length of the entire
this,
contour
is the length of the individual arcs added together.
No.
Now, why are you saying no?
Because some of them overlap.
Okay, because there's some overlap. Here's the thing. Remember when I said yesterday that this is different than just having the arc on the board at one time? This is like driving to the store. You have to do it. Okay? If I drive to the store and then I drive home, of course I'm in a different lane, so you say, okay, that's certainly a different path. But then I forgot the eggs. So I have to drive back along the same road.
Did it take no time to get the eggs?
We're not going to worry about that one little problem. Yes, of course I would have to stop the car, you're right. But let's assume that the eggs get thrown in through my window right as I get to the store.
No. What I mean is, did it take no
Right.
time to retrace your steps and go get the eggs?
Yeah.
No, it didn't take no time.
Well, that's why you double count.
Right.
Mm-hmm.
Well, yeah, and that's the same thing here. This is not taking no time either.
That was my point.
Yeah. Yes, this is... Sorry, I thought you didn't make a statement. All you had was a question, so you can't have a point. My wife and I go through this all the time.
That's not work, right?
A question is not a statement.
It can be.
It
Why
can be a
not?
point.
Interrogative, declarative. What? Have I gone mad?
Yes.
With the question, you could be proving a point.
Yes.
Yeah,
No, you
exactly.
could be. No, you might be implying something. In the person's brain, they might be making connections, but that's not making the point.
Fine, it's an implication.
There you go. So,
That was my implication.
so the point here is that when I go around this circle, this is taking time, and when I go around it the second time, I have to go around it. It's taking.
You have to go that distance.
I have to go that distance. If I was
It's like
driving
you
a car,
miss your
I
turn
have
off
to
on
go
the
that
rotary.
All of them are different.
You miss your turn off on the rotary.
What's
and
that?
You have to go around again.
So you do. So that's the length of C is going to be the sum of the lengths of gamma. I'll use L of C for the length. Okay, so that's what it should be. So the only reason that that's relevant to me is it means that if I want to compute the length of C just abstractly, I only have to compute the length of a simple smooth curve, not the length of a piecewise one. If I do one, I can just add them up. So then the question is how, if I have 2 points and I connect them, right, so here's Z of A and here's Z of B. How do I find the length of that curve? So in calculus, we did it in at least a special case, y equals f of x. You had some formula. You integrate from a to b, square root of 1 plus the derivative of y with respect to x squared dx, right? Something like this. Okay. So it's a little different here because we're starting with something that's just defined in terms of t, right? It's sort of a parametric sort of deal. But the principle is exactly the same. We're going to define a function. S of t. Right? So remember again, A is less than or equal to t is less than or equal to b. And S of t is going to be defined as how far you've gone along this path at time t. Okay, and I don't mean z of t, which is the point that you're at. S of t is really the arc length. We don't know what it is, but whatever it is, it's S of t. Okay, so at time t, you will be at S of t, and S of t, I should say, is this distance. It's not this point. So here's z of t. This arc length is S of t. You should always wait to draw it until after I've done it. I take several iterations. Now, because we know from experience that answering questions about arc length comes down to exactly the sort of considerations that you had to do when you were considering area, we're going to what? We're going to take little pieces and pretend that they were straight lines and then add them up and then make those straight lines really tiny but have more and more and more of them, and then eventually we get an approximation, and in the limit we actually get the exact value. Right? That's the general idea that we always go for. So to do that, let me pick a point which is a little bit away from t. I'll call it t plus delta t. And so
You knocked it over.
okay, so S of t plus delta t is the length of that red line.
Just killing it, man.
Okay. Does anybody take the red line?
Yes.
The red line is so much better than the green line.
It's the best line, actually.
Oh yeah.
Okay.
Line sucks.
Now,
Yeah, there are the
All
famous
the lines
creepers on the red line.
All the lines like the size of the red line. So by far the best line ever.
Oh yeah, and it's fast.
Yeah. Green line, forget it. That's on the bottom of the
Green
list.
lines.
The
Blue
green
line,
terrible.
who takes
The orange
that
line is even better than the green line.
I want you to notice
I think
something.
Better than the green line. What did you have to say?
Two things, actually. One, this is exactly what I was talking about when you write these stories, that you don't want to put in something that makes the person think about something else. I draw this nice picture on the board, I got everybody's attention, I mentioned the red line, all of a sudden everything about now I see, now I really like taking the red line. You know that one time though, I got mugged on the red line and I lost my Duran tape. Oh, remember when they used to have tapes? That was great. I used to have this cool Walkman. It was so great, but then the battery melted in it, and like the battery acid dripped out, and I ended up opening it up, and it burnt a hole in my jeans. Those cool Levi jeans that I had to throw away because of that hole. And then I felt like, wait, should I throw it away, or because I know it's coming back in style that you have these holes in your jeans.
Oh, yes.
Do you see what happened? And it just keeps going. All of a sudden, you realize. He's gone like 10 minutes and I don't know what he's been talking about.
That was my English class last
Wait,
semester.
can I just do a side comment though? Did you guys read about the handicapped guy that went from like all the lives?
Yeah, I did.
I
I got
was-
off at every stop
Every
and
stop
waited for the
and
next
then waited for the
train.
next train and then got back on.
It
And
took
they
him,
did
like,
it for
16 hours
every
or something.
line. Every line.
It sounds like he's handicapped.
No, I mean like he
No,
was
that was
doing
his
it
goal
as
in
a
life, yeah.
statement
Yeah.
to other handicapped people to say that they can ride the T.
Oh, okay.
I was
Cool.
kind of sad that I didn't see him though. I kind of wanted to talk to him on the red line, but we missed.
Oh
each
my
other.
god, on the orange line once.
Okay, so let's try to focus.
I came up and he's like, do you have any cheesy crackers?
I saw him when I was meeting my friend today. He's like, who is that guy?
I've lost the class.
No, it wasn't Spare Change guy. It was,
He has a
He's
Facebook
awesome.
page.
This is
though,
an
right?
example of when you're
So
teaching
awesome.
what not to do.
Okay, can I tell you? No, sorry, this is only the last one. I got so mad at him actually, and I almost went up to him and yelled at him because 2 days in a row he said it was his birthday, and I said, people are not going to give you money if you're lying to them. I was really mad. I almost went up to him and said that. I said, I'm not going to give you money now because you lied. Poor Spare Change.
He is not boring.
That was my quick side comment. We can get back to class now.
Alright, so speaking of core change guy, if S of
What?
t
No, it's
plus
spare
delta
change.
t is
Spare
here,
change guy. Gee.
and this, if I subtract the arc, if I subtract S of t plus delta t minus S of t, then I'll get this red bit in between these 2 points.
In the green bit.
No, I want the red bit. I really mean the red bit.
Wait, what?
If I take S of t plus delta t and I subtract S of t, okay, so the S of t plus delta t is this whole red bit.
Look at the green.
And if you subtract this blue part, the S of t, then I'm getting the red that's left over. It's kind of covered up by the green. Okay? Why am I not getting the green?
Because the green line sucks.
What's the difference between the red that's connecting these dots and the green that's connecting the dots?
The blue.
The green
Because
is
you're
a different
S of
function.
t.
thing, yeah.
Let's
Are you
zoom in.
including S of t in one and not S of t in the other?
Nope, no,
In
here's,
the other?
let me zoom in on this, okay, and show you what's really going on. Okay? So this will be z of t. And when I zoom in on this, here's z of t plus delta t. When I zoom in, the red looks like this.
Oh.
The green
Yes.
looks like this.
Yes.
The green looked a lot better the first time. Right. What's the difference? This green is a direct line. The green line goes directly.
I wish it did.
The red line is roundabout, right? That actually is following the arc. That's following the curve. The green is the straight, that's the straight shot, right? It's the vector going from z of t
Right.
to z of t plus delta t. So what's the length of the green line?
Less than that of the red line.
True. But we can actually, we know what this distance is.
It's the
Oh, it's
Square root.
it's z of t plus delta t minus z of t over delta t.
Oh, that's so close. That's not the distance. The distance is you take this point, you subtract it. That gives you another vector. I mean, that gives you another complex point. You want
Square
not the square root. You want the norm,
Norm.
right? The norm of the difference. Just like when you take the absolute value of the difference, that gives you the distance between two numbers. How do you get the distance between these? Take the absolute value or the norm of their distance of the
I
difference.
did the slope, didn't I?
Now, what happens if I consider the quotient? This one divided by this one. As delta t goes to 0. Yeah.
The equation that's up there right now is for the green part.
This is the green. That's the green.
Oh.
That's the red.
So you have
And
derivative.
then divided. So what's the equation?
What's the
whole
equation?
thing, like the
This
red
is this
divided by the
is
green.
this is not. I'm actually just ad hoc putting the red divided by the green. Right? Because I want to ask the following question: as delta t goes to 0, what can you say about the red versus the green? What do they start to look like?
0.
Though they're both numbers,
They're equal.
they start to look like they're equal, right? That's the whole point of doing these limits, right? Is as you get these points really, really close together, this red thing, I mean, if you put the dot here, right? If that was your z plus delta t, the green would go like that. It'd look almost just like the red. Of course, you zoom in on it a lot, and it starts to look farther apart again, but then you move that point even closer, and it starts to look a lot like it. And as this delta t goes to 0, these two numbers should become the same. Right? So taking the straight shot or taking the curve doesn't matter as much if you're looking really, really, really close together. So this thing should go to 1 because they're both going to the same number. Okay, fine. If you believe that, then I've got you.
What if we don't believe it?
Then get out.
Alright, let's go, Christina.
Can't believe it's
Class over, guys.
Can't believe it's not butter.
So,
What?
we're going to compute
What's not butter?
the derivative of s of t. Okay? What's the definition of the derivative? That's all we have to remember, right? This is really easy. It's the limit as delta t goes to 0, s of t plus delta t minus s of t over delta t. So we're going to play a game here because we don't know what to do. We don't really have any information. You can play.
Yes.
And here's how it's going to work. I'm going to multiply and divide by the same number.
That's pretty cool.
Okay? So this is going to be one of those I'm brilliant moments.
Wait, you are?
Not really me.
Oh.
Alright? But
Us?
no, it's whoever first really thought of it. But it's one of those things where, yes, with experience you'd probably think to do this, but if you've never seen it before, you go, why in the world would you ever think to do that? Alright, it's the same reason this is, why was I writing this down? Well, you're going to see. I wrote that down because I knew that I was going
The red line's the top of that.
Oh.
Okay. There's delta.
And what happens as delta t goes to 0 to this first term?
That goes to
One.
1.
Goes to 1. So then you're just left with this. And what is that? It's just
Number?
it's just the norm of the derivative of z.
Over 0. It goes to infinity.
No? The derivative of z, alright, is this thing. If you didn't have the norms there, you tell it's just the derivative of z. Norms you can pull outside the limit if the limits exist. This part is 1, and this part is dz dt with norms. So this limit is, I feel like just the norm of dz dt. Okay. So this arc function, right, this arc length function, whatever it is, its derivative is the norm of the derivative of the actual function z. So that's already nice. We've somehow brought it back to z. How do I get s, though? I want the arc length function itself, not the derivative. Well, if you have a derivative and you want to get rid of it, you integrate. We have to use the fundamental theorem of calculus. Tells us that our function s is going to be given by, well, you integrate over the region. So we're going from a to b. The derivative of ds dt times dt. But of course we know what ds dt is. It's the norm of dz dt. Or the absolute value. However you want to say it. There's another way to write this. it's going to start looking a little more familiar. Well, the derivative of z is x of t plus I y of t. And we said the derivative of z is just do the derivative of x plus I times the derivative of y. So we could write this as the norm of dx dt plus I dy dt. Yep, that's the very first thing that we wrote on the board today, I think, or nearly the first, after the Jordan curve theorem stuff. All right, it's right at the beginning, except I wrote it as z of t equals x of t plus I y of t, and I said z prime of t equals x prime of t plus I y prime of t. Now the only difference is that I'm writing dx dt instead of z prime. How do you find the norm here? Well, this is actually really easy because I've broken it up into the x component and the y component, right? Or the real and the imaginary components. It's just going to be the square root of the sum of these squares. So when I go down here, I can write this as the integral from a to b, the square root of dx dt squared plus dy dt squared dt. So this is the length of our contour, or gamma, say. Say if we just have one simple smooth curve, that's our length. So the upshot is that we have a formula. The downshot is it sucks because it's got a square root. Square roots and integrals are sometimes tough. But you remember all those integral tool challenges, right? And when we start sticking square roots there, it could be really hairy. Okay. So this L of gamma is the length of gamma. Okay. Questions? We have 13 minutes left in the week, so yeah. So let's start. Well, I'll pause for station identification. Then we can start talking about line integrals. Hi, what's up?
Are you going to correct all the problems and the homework that you gave us for this week? There's a lot.
Right,
Like
40
of them.
40 problems?
Yeah.
Yeah, I remember we counted up at 22. Well, I intend to. If I can't, then I will not. By definition, either I can or I can't, and if I can't, then I won't. See, if I could and I didn't, that could happen, right? But it doesn't have to happen. But if I can't and I don't, that's redundant. If I can't and I did, that would be phenomenal. Okay, so let's get back to line integrals. And I think we had started mentioning these things before. And we even wrote down it for the real plane, just to recall things a little bit. We didn't talk about the vector valued version of a line integral, but at least get some feeling. So I was just going to write it down, but this time for the complex numbers, just so that you keep seeing it over and over again and realize it's nothing all that complicated. So what I'm going to say, I'm going to first say for simple smooth curves, and then we'll extend it to contours in an obvious way. Namely, we'll do it in pieces. So I have a function how should I say this? I have a curve C, or gamma. We'll use gamma. I'll use gamma when I'm just going to use a simple smooth curve. So I have a gamma, and I choose an admissible parameterization. Okay, so that implicitly is assuming that there is such a one, right? But there should be a simple smooth curve. Okay, so gamma has a direction there. Admissible parameterization Z of t, where t sits between A and B. And now, so this is sitting in the complex plane, and so I might have a function. I might have some function sitting around f of z. And I can evaluate f, assuming, well, we want that gamma sits in the domain of f. Right? Say gamma sits in the domain of f. And when I say that, I mean the points of gamma. Okay, they're all in the domain. And I can evaluate, if it's in the domain, I can evaluate the function on this curve. Now you should have in the back of your mind the real case. Right? Just take the very basic one. You have the real number line between A and B. That's a simple smooth curve. Right? And you have a function where that interval is in the domain, and you can define the function on that interval, and it takes on values. Okay? And then what did you start doing? You started looking at breaking up that line into little partitions, and then you took points from each of the partitions, and then you multiplied the width of the partition times the value of the point, and then you added those up, and then you took the limit as the number of the points went to infinity, right? The size of the partitions got smaller, and that's what you define to be the integral. Well, we want to do exactly the same thing. You just have to know the story. Okay? If you know the story, you can figure out what this is supposed to be. Okay? So the story starts with dividing up your curve, right? We had to start with the interval, we divided that up. Well, we're going to divide up this thing. So we pick points. Divide the sucker up. Then within each of these, well, you have something. You have the arc length. Each one of these gives you a certain arc length. So what are we going to do with that arc length? Well, that's going to be the width of our interval, right? When we drew rectangles, what did we do? We took the rectangle, the base was the width of the interval we chose, and then the height was the value of the function at some point in that interval. Well, here the width is just going to be the length of the arc between these points. Now we're going to choose a point in there. Say we choose a point right there. And we can evaluate f at that point. And we draw a sort of pseudo-rectangle. It's not really a rectangle, but that's the way we think about it. Okay. We take this point, say this point is, we'll call it, say, zi. Okay. You evaluate the function at zi, and then you multiply by the length. So let's say the length here is s sub I. So you'll multiply this by s sub I, or maybe we'll call it delta s sub I, so it looks like a small change. Okay. So for each one of these little gaps, you're going to get something that looks like this. And again, this is just coming from the real situation. This is the area of a rectangle when you're talking about the real ones, right? That's the base of your rectangle, that's the height. It's exactly how we defined the definite integral. You happy about that? No. Let's draw a picture. This is important, and it's important because I want you to understand the definition. right? Because every definition that is ever done about the integrals looks like this, right? At least sort of this Riemann integral style. They all look the same. They all have the same idea. The only difference is in the physical interpretation and some of the specifics. For the complex, the physical interpretation will be more complicated, but we don't worry about that. Let's go back and just handle the very basic real case again. How did we do it? We took the interval AB and we divided it up into segments. And each one of these segments, there was a base, there was a length here, right? And that was maybe delta xi. Then you chose a point in there. And you took the value at that point. So this maybe is xi star. And this point up here, right, on the y-axis would be f of xi star. Okay, so you take the value. And then you draw a rectangle whose height is that point right there. And the area of that rectangle is the product of the base and the height. So this rectangle has area f of xi star times delta xi. Is that right? And then how did I get the whole thing? Well, I added up all of these things. So I threw a little sum on the front. And then how do I get the exact value? Because this is just an approximation. I took a limit. Right? As the number of these things went to infinity and the size of them went to 0. Okay? So we do the exact same thing. Right? The only difference is that here, we did this because we were trying to compute the area of a rectangle. And that's how we define things. Here, we're not trying to satisfy some physical intuition. We're just trying to mimic the definition. So what we're going to do is write down the integral over a path gamma. Okay, so before we had integral, this here was going to be the integral from a to b, f of x dx. Here we're going to do an integral over a gamma, that's like a to b. And it's going to be our function f of z dz. And this is going to be a limit as, well, we could take the number of these things, but I liked this notation we were using the other day where we look at partition sizes. Right? So if this is one partition, we make the partition size go to 0. But it just means the same thing. The number of these partitions goes to infinity, the size of each goes to 0. Right? You should sum up, right, from, say, I equals 1 to n, if there's n of them. And then it should be f of zi star. So you're choosing within each segment one point. Doesn't matter which one you choose. Okay, you just choose a point. That's a zi star. Well, that would have been a zi star. That would be a zj star. Okay. So you evaluate the function at that point. That gives you the height of the rectangle. There's no rectangle, but it would be the height if it was. Times the width, right? And that's the change in this arc length.
Wait, what do you mean by this star?
It's just notation. It's not meaning anything special. It's a point within the ith gap, right?
So your z over there by your delta si hat, that's a z star.
Yeah, that's what that is. Yeah, it's a star.
Okay.
So we'll go back and do this again on Tuesday, because it takes a couple seatings. But okay, so this is going to be a definition of a line integral. And it'll be very easy. This was just one simple smooth curve, but it'll be very easy to extend this to any contour. And we'll do that next week. All right, so we'll restate this again. And then, of course, what's the real thing going to be? The real thing is, it's easy to write down these definitions. You just copy. The problem, and this is exactly the same problem we're going to have in 265, how do you actually compute it? You don't want to use the limits, right?
Is it redundant to restate things again?
No.
What?
No, certainly not. Because you can restate things over and over again.
Yeah, but then it'd be 3 or more.
Pardon?
It'd be 3 or more.
Is that-
So if you haven't done 2 yet, kind of redundant to restate things again.
I used to use this.
Oh, you mean the second time?
I mean, used to buy
I suppose
several
it
columns.
depends on if you just mean within the class or in my life.
You don't like these, don't come in packs and try.
Never mind, I figured it out.
Okay.
Oh, what
And I use the
is
pink,
sign H?
blue, pink, green, silver,
Uh,
gold.
Yeah. No.
would you like to tell me what H?
A lot of
It's so
color.
long.
Sign
Yeah.
H.
Oh, the hyperbolic sign. I'm sorry, cinch. Yeah,
Like he used
you don't
color
mean
pencil
sign of H. You mean on the homework.
I used to
when
use
it's
color pencil.
cinch.
Yeah, I've never seen that before.
So you have a
That
pack
I know of.
Like 7 to 9 colors.